Okay, I think we can resume with Oscar's third lecture.
Thank you. So we have been discussing in my other two lectures about vortex equations, abelian and non-abelian vortices, and their algebraic geometric avatars in the moduli spaces of pairs, triples, chains, and all that. And we saw how these things arise from, as dimensional reduction from vector bundles on this complex surface consisting of the product of the Riemann surface by CP1. But I said yesterday that, in fact, my main motivation to study these objects came, in fact, from the theory of Higgs bundles. And so let me tell you a bit about that. So X is a compact Riemann surface, as all the time here. And so Hitching, in his first paper on Higgs bundles, introduced these objects consisting of vector pairs consisting of a holomorphic vector bundle on X. And then phi, the Higgs field in this case, is a homomorphism from E to E tensor K. So it's a twisted endomorphism of E, where K is the canonical line bundle, right? And so there is, if you're familiar with the notion of stability of vector bundles, there is a natural notion of stability here, which is numerically the same condition, except that you only check for subbundles that are invariant, are left invariant under phi, right? And with that notion of stability and polystability, you have the moduli space of polystable Higgs bundles of rank n and degree d. And this is a moduli space with tremendous interesting geometry. And one aspect that, it's a hyperkähler manifold and complete integrable algebraic integrable system. The one aspect that interests me the most for a long time has been to do with the Nonabillian Hodge correspondence, and in which one of the pieces is, in fact, what originated this moduli space, the study of Hitching equations. And again, I'm formulating Hitching equations here as an equation for a Hermitian metric, H on E, right? Of course, you can always think of this as equations on a connection on some unitary bundle and some Higgs field, which is in the adjoint representation, okay? And these equations indeed originated from, again, a dimensional reduction procedure by studying instantons in R4 and reducing in two directions, considering instantons that are translational invariant in two directions. Hitching ended up with these equations on R2 and observed that they are conformally invariant, so they make sense on any compact Riemann surface. Once you have them on any compact Riemann surface, it has been, and still, an open problem to show whether these are dimensional reduction in the same spirit as the vortex equations are. We haven't been able to solve that. It's been a long time doing that. But so one of the, as I say, important motivation is the relation of the moduli space of Higgs bundles with what we call the character variety of the fundamental group of X, that is representations of the moduli space of representations of the fundamental group of X in this case in GL and C, right? And so this is the Nonabillian Hodge correspondence. I mean, if we want to consider, you see, if you have, sometimes we see these equations with mu equals 0, right? And this is because that corresponds to degree 0. If you want to study any degree, then you have to put this central thing here, right? And I mean, you can think of this mu as just, is really like the slope of the bundle times a Kähler form, right? And so this is the Nonabillian Hodge correspondence, and one is interested in studying the topology of these moduli spaces, and in particular, because there is a lot of interest in studying the topology of the character varieties, right? And a strategy that was indeed used by Hitching himself in the case of rank 2. I mean, in his paper, this first paper, he only considered the case of rank 2, right? And but the whole thing, same ideas. And so this strategy to study topology is studying the fixed points under a very natural action, C-star action that one has in the moduli space by rescaling the Higgs field. And so the fixed points, this action and the fixed points are the key to study the topology. And the fixed points, you can first, you notice if phi is equal to 0, then that's a fixed point. So you have inside the fixed points subvariety, the moduli space of bundles itself, right? And then you can easily see that if you have phi different than 0, the other fixed points are actually correspond to Higgs bundles where the vector bundle decomposes as a direct sum of vector bundles of a smaller rank, and the Higgs field goes from one to the other, is some nilpotent Higgs field. And so in other words, there's like a symmetry breaking to a product of the unitary product of unitary groups. Now, so these are exactly the moduli spaces of chains. I mean, in the moduli spaces of chains, you have to excuse me. Moduli spaces of chains depend on parameters. The stability depends on parameters. We saw that in the case of triples, for example, quite concretely. And these objects, these chains become Higgs bundles for a certain value of the parameters. That is exactly where they can live in the moduli space of Higgs bundles, right? And so this, as I say, the topology of this is encoded in this, and there are, if you want, two main different ways of doing this. If, for example, R and D are coprime, I mean, you can see this actually in the coprime situation where the moduli space is smooth. You can do Morse theory, which is what Hitching did in the initial case of rank 2, where in fact the Morse function is the L2 norm of the Higgs field. You solve this equation, you have a Hermitian metric on your bundle, and so you can compute the L2 norm of the Higgs field, and that turns as a function from the moduli space to R, and that is a Bott-Morse function. And so the critical subvarieties, you can now compute the Poincaré polynomials in terms of the critical subvarieties, and the critical subvarieties happen to be the fixed points under this C-star action. So that is how Nigel Hitching computed did this to compute the Poincaré polynomial of the moduli space. And there, because he was doing the rank 2 case, you could see that, in that case, this object is just a sum of two line bundles. And so phi is just a homomorphism from a line bundle to another line bundle tensor K. So at the end of the day, it's just a line bundle and a section of that line bundle. So vortices. So vortices and symmetric products of the curve appeared in there. And he was able to compute the Betti numbers because McDonald, many years before, had computed the Poincaré polynomials of the symmetric products, okay? And so same strategy was used by Peter Gotten, where now, because one is in rank 3, one can see triples, 2 of rank 2, 1, 1, 2, and then chains of 1, 1, 1, and so on. And the same Morse theoretic strategy were here, always in the coprime situation where the moduli space is smooth. And so this was extended in my work with Jochen Heinloth and Alexander Schmidt for actually arbitrary n. And there we took a more algebraic approach, which is equivalent to the Morse theoretic approach, in which you compute the Grothendieck motif of the moduli space. And the Grothendieck motif has, in particular, the Betti numbers and a lot of more information. And so there, you do a localization procedure, which is equivalent to Morse theory, but is goes under the name of Galiminsky-Virula localization. So at the end of the day, the point is that the computation of the motifs of Betty numbers of the chains will give you, yeah, the Betty numbers and more information, the motif of the whole moduli space of Higgs bundles. And also, the study of the geometry and the topology of moduli spaces of triples and so on enabled us to, in fact, say things about homotopy groups of the moduli spaces. And I want to say something about a direct application of the moduli space of triples to the case of Higgs bundles that have this specific form. These are Higgs bundles in which E is a direct sum of two vector bundles. Say this is of rank A and this is rank B. And the Higgs field has this off-diagonal form where beta is a homomorphism from W to V tensor K, and gamma is a homomorphism from V to W tensor K. And so you want to consider this this sort of moduli space, you know, under suitable equivalence. And why on earth would you be interested on this? Is because this moduli specific bundles corresponds to another important character variety. And this is the character variety for the groups, the real groups UPQ. So these are correspond to, yeah, so homomorphisms from the fundamental group of X. Well, if you want to accommodate any degree, so that the direct sum of A and B is any degree for E, then you have to consider the central universal central extension of the fundamental group. If you are happy with the degree being 0, then that's the fundamental group. Going to UPQ, modular conjugation. And so it turns out that actually when you study this moduli space and you apply these Morse theoretic techniques of hitching, the minima of the Morse function are in fact given by Higgs bundles like this, in which beta is equal to 0 or gamma is equal to 0. It depends on some topological invariant that I will mention now. Question? These are, sorry, this is stupid. This is P and this is Q. Thank you very much. A and V will be the degrees, right? So this will have degree A, and this will have degree, the degree of V is equal to A, and degree of W will be B. This is what I meant. So the P and Q are the ranks. Yeah, yeah. I will now, the degrees will play now a role, but the minima is B equals 0 or gamma equals 0. So these are exactly the triples. You know, it's something like this or something like this. So the minima can actually control things like the number, you know, the connectedness of the counting connected components, or can and are useful to compute higher homotopy groups. And that was one strong motivation to study the moduli space of triples that I presented yesterday. And so in this, I want to actually mention a relevant topological invariant in this. Once you have a Higgs bundle like this, it's called the Toledo invariant. This is AB, and this is twice AQ minus BP. So you have now the ranks and the degrees of V and W appearing, P plus Q. And there is, shouldn't be going beyond this. So there was an important bound that had been found initially by Milnor in the case of U11. This is, it's called Milnor-Wood inequality. Milnor-Wood inequality that establishes that this number is smaller or equal than, in fact, the minimum of P and Q times 2G minus 2, where G is the genus of the surface, right? And so what we showed, in fact, we actually proved this bound from the point of view of Higgs bundles, which is a consequence of semi-stability simply. And we proved that for any value of this Toledo invariant, there is just one connected component. And so this was one of the main applications of the study of the moduli spaces of triples that I presented yesterday. But we also were able to give more information about homotopy groups. Okay, so let me go on. And in this story, it's exactly the whole philosophy is that in these problems, like the moduli space of triples that we saw yesterday, there are parameters. In fact, there was a real parameter. And those parameters play a crucial role in the study, as well as in the study of this motive, this Grothendieck motive in general, because you are interested in the moduli space for a certain value of the parameter where the thing is a Higgs bundle, right? And that value is somewhere in the middle of this interval that I presented yesterday. And you have no idea how that thing is. And it's exactly there that you apply the strategy of understanding the large moduli space and then do the crossing and realize that, you know, that the codimension of the things that you have to remove and add is big. And so that doesn't affect connected components or higher homotopy groups up to a certain degree. Yeah, so that's how you do it. Now, yeah, so I want to now discuss about Higgs pairs in general. So in the first lecture that Nuno gave, he presented vortices in a rather general setup that you had like a G bundle for a G compact, and then a action of G on some Kähler manifold and some equation that was moment map and it was moduli space of vortices. Or in a more the algebraic counterpart, if you want. So you have a reductive complex Lie group, G, with Lie algebra G, and then you have a representation of G in a complex vector space. I actually here will care only about Higgs fields that take values in vector bundles. Okay, so of course the modular situation is very interesting, and I am a great believer. In fact, it was the subject of the thesis of my first student, Ignacio Mundet, precisely replacing V by any Kähler manifold, and that has been very fruitful and relates to many topics that will be discussed in this meeting. But I want to focus on just representations on vector spaces. And so just to introduce some terminology that I will call a GV Higgs pair. It's a pair where E is a holomorphic principal G bundle, and V is a holomorphic section of the associated vector bundle to the representation that we have, rho. And here we want to consider, want to be more flexible. And so you can twist by a line bundle. And I choose to twist by the canonical line bundle because of the relation to Higgs bundles that we will see. But this could be any line bundle or even just the trivial line bundle. So there is no twisting. This is exactly what appears in the vortex triples, chains, and so on, right? So what I want to do today is trying to convince you that you could take any representation raw, but there are representations that I will just consider appropriate to generalize vortices. And what do I mean by generalizing vortices? That have similar phenomena. On the one hand, I want my moduli spaces to be compact. I want the stability depend on parameters, and I want similar kind of story about how you can relate for different values of the parameter. And so in any case, in full generality, whatever V is, actually what I'm going to say to some extent works even for V, which is just a Kähler manifold. But there are suitable notions of stability for these objects. And they depend on parameters. The parameter being actually, let's call it sigma, is an element, if you take the center of the Lie algebra G, and you decompose it in the in the two real and imaginary part, the parameter takes values here. This is what happens in the vortex situation. And so then you can construct the moduli space of sigma polyastable GB Higgs pairs. And I will just use for the particular value of sigma equals 0, then we won't put here any sigma. This moduli space is actually the construction of Alexander Schmidt that I mentioned yesterday works in this generality, providing, in fact, a GAT construction of these objects. Now, a particular case, actually, of this kind of Higgs pairs is the case of Higgs bundles, indeed, where V is just the adjoint representation, right? And I talk about G Higgs bundles, not just the Higgs bundles for GL and C, which we were expressing in terms of a vector bundle and a twisted endomorphism, right? But just as a G bundle and a section of the adjoint bundle tends to the canonical. And for this moduli space, I won't put MG and the Lie algebra G, but just MG. It's a moduli space of polystable G Higgs bundles. And here it's important to notice that actually, while in general, for any representation, an arbitrary representation, there is a parameter of stability, this sigma, that is there. In the Higgs bundle situation, that parameter is fixed by the topology, because if you go back to one way of seeing this is if you go back to the equation, to Hitchin's equations, you notice, the parameter will be something here. But when you take the trace of this equation, the trace of this evaporates. And so again, this parameter is determined by the degree, right? So there is no parameter in the moduli space of Higgs bundles. Yeah? It's just fixed by the degree of the bundle. But for an arbitrary representation, depending on the representation, then you do have parameters. Okay. So this is what I said before, that we could have twisted by any line bundle, in particular the trivial line bundle, and then we will just be, in the situation, the vortex situation that we have studied, and we consider K because you will see this pair has been related to the moduli space of the Higgs bundle. So now, coming to my question is, what representations have the right to be leading to something we can call vortices? This is, of course, very subjective, right? But as I said before, I want my moduli space of vortices to be compact and to depend on parameters and generically be smooth and all the properties that we have seen in the case of triples. And this, it took me some time to realize that actually this relates to what I call pre-homogeneous vector spaces. You may have encountered these vector spaces, but let me tell you about it. Were studied by Mikio Sato in the early 70s. So you have G, a complex reductively group, and so then we have a representation of G in a holomorphic representation on a complex vector space, right? So you say that V is a pre-homogeneous vector space for the action of G if there exists an open G orbit in V, and let's say omega. And necessarily, this open orbit has to be is unique and dense. You can easily show that. Now, let me tell you a few things about pre-homogeneous vector spaces. So this is called pre-homogeneous, obviously, because this open orbit is a homogeneous space, is the quotient of G by some isotropy subgroup, the isotropy of any point in omega, right? That's why they're called pre-homogeneous. So the only place where they fail to be homogeneous is in some singular set, which we call S, which is just V minus this open orbit. And so there is an important notion here in pre-homogeneous vector spaces that is the property of being regular. And you say that a pre-homogeneous vector space for the action of G is regular if the isotropy or the stabilizer is a stabilizer of any point in the open orbit is a reductive group. Yeah? So otherwise you say it's non-regular. Some examples. So first example is the case of taking G, GL, and C and the standard representation, the fundamental representation. In this example, the the open orbit is just the whole vector space minus 0, right? Null vector. And this, you can see, is regular only when n equals to 1. Take a higher dimension, then the stabilizer subgroup is always a parabolic. And that is the main example of non-reductive groups, right? Parabolic subgroups. Another example is that of taking the vector space of matrices, P times Q matrices, is a pre-homogeneous vector space for the action of GLP cross GLQ. And the action is given like this. Yeah. Take a matrix here, you just act by A here, and then by Q, the inverse of Q here. And there, the open orbit is, easy to see that those matrices here whose rank is the minimum of P and Q. And the example is regular only when P is equal to Q. And of course, I'm sure you have already realized that these two examples correspond to the vortex equations for the Bradlow pairs, including the abelian situation, right? The first vortex equations that we mentioned, abelian and non-abelian, and these correspond to the case of triples, right? That exactly the case of triples correspond to having a bundle, principal bundle whose structure group is this, and the Higgs field takes values exactly in this representation, right, in MPQ. So these are our basic inspiring examples. So now, okay, there are a number of properties of pre-homogeneous vector spaces that are very interesting and help you to detect when in fact, a pre-homogeneous vector space is regular or not. In particular, this condition on the singular set, so the V minus the open orbit, the vector space is regular. The pre-homogeneous vector space is regular if and only if this is a hypersurface. So this immediately helps you to understand, to detect without making any computations or few computations when something is regular. So one important ingredient in the theory of pre-homogeneous vector spaces is the existence of relative invariance. This means non-constant rational function from the vector space to C that for which there is a character of the group, yeah, a character, so a homomorphism from G to C star, so that this function behaves like this. If I act on X by my element G using the representation, then that's not f of X is not invariant. F is not invariant, but it's actually invariant up to multiplication by this character acting on G. So this is one of the important things about pre-homogeneous vector spaces is that there are no invariants. There are no G invariants except the constants, right? For example, the adjoint representation is not a pre-homogeneous vector space. In fact, the whole, the invariants of G invariants of a Lie algebra are the basic ingredients to define the hitching map. And this is exactly, so there's nothing like this. So if you want to define a hitching map, all these things go to 0. And this is why the modular space is compact, right? But there are these relative invariants and for some characters, right? And they will play an important role in the story. And so this relative invariant is uniquely determined by its corresponding character up to a constant. Yeah? And from here, you can deduce that, in fact, these functions are really homogeneous functions, right? Not necessarily a polynomial, it's a quotient of polynomials and so on. But, and so you can also, in terms of this, if I give you a character, we know what are the characters of a reductive group, right? And I ask you, can this be the character for which there is a semi-invariant, a relative invariant? Not all characters are actually candidates to have a relative invariant. And a test is that there exists a relative invariant for this character, if and only if the restriction of this character into the isotropic group of any element in the open orbit is trivial, right? And so, so there is now the problem of identifying what are the characters of the prehomogeneous vector space. Okay, so this is so it's a very beautiful theory that shows up in many contexts. But here is, let's go to and give you an example, coming back to the regular case, the case of PQ matrices, but when P is equal to Q, right? I want to, this was example 2, the case that appears in triples, right? But where the 2 bundles are equal, here is a relative invariant is the determinant of the matrix. And the character is given by the character of, you know, this we are talking, remember the group was GLP, in this case is GLP cross GLP, right? Is the determinant of A times the inverse of the determinant of V. And you can just compute that because of this property, the determinant of a product is a product of the determinants. You can check that this is indeed a relative invariant. And this relative invariant is the key of many things that happen in the study of triples. And but now, so now, okay, this is the family of vector spaces that of G vector spaces, vector space with a representation of G that we care, prehomogeneous vector spaces. But there is yet a more restrictive class, not very restrictive, but a class that we will be particularly interested in. Particular, the cases that we have seen, example 1, example 2, fall into this class of prehomogeneous vector spaces. And this prehomogeneous vector space are produced as follows. So we start with G, a semi-simple complexly group. This G is not the same G of the previous section. It's a semi-simple. I mean, you can do for reductive, but it just take semi-simple complexly group. And now we give a name to the killing form because we're going to use it, as you'll see. And so let me tell you, remind you what a set grading of this semi-simple complexly algebra is. A set grading of the algebra is a decomposition of G in summons G sub I for any integer in Z. Obviously, since these are finite dimensional, after some value, these are 0, right? And that satisfy the property, this Lie bracket property. You take Gi, Gj is in Gi plus J. This is a set grading. In particular, notice that G0 is a Lie subalgebra, right? Because G0 goes to G0, so the Lie bracket makes sense in G0, not in the other terms, right? But G0 is a Lie algebra. And in fact, one can show that any grading of a Lie algebra is, when I give you a grading, let's say I give you this grading, there is always an element, zeta, in G0 that we call the grading element, which realizes the subspaces as the elements in G, right? Sorry, this should have been a small x, not capital. So these are the elements in the Lie algebra G, so that by the adjoint action of this zeta, we have I times x, right? So these eigenspaces for the action of zeta. And this always exists, this grading element will play a crucial role in the story. No, so now, if I called, let's say G0 be the centralizer of zeta, but if you want, you can think of G0 as the analytic subgroup corresponding to, okay, if you want it to be connected, but sometimes it's not connected, but is a Lie group corresponding to this algebra, right? So this thing, because G0 and J is in Gj, is actually saying that the adjoint action of G restricted to G0 preserves all these GIs. So all these GIs are representations of G0. And G0 is indeed a reductive group. This is a property about a centralizer of some element. This is a reductive group. It may be non-connected, but it's a reductive group. And so GIs are acted by G0. And here is the important property that is due to Wingberg, that except for I equals 0, right, then all the GIs are pre-homogeneous vector space for the action of G0. And I said G0 is not, because G0, this Gothic G0 is the Lie algebra of this. And I said the adjoint action is never pre-homogeneous because there are invariants, right? And so you have no rights to have invariants, right? All right, so these are the pair consisting of G0 and a GI for I different than 0 are our pre-homogeneous vector spaces. And these will be providing a vast generalization of moduli spaces of vortices that will comply to the properties that I have been describing in the case of triples and so on. Now, so let me tell you about some recent work that I have done with Olivier Vicard, Brian Collier, and Domingo Toledo. And will appear published very soon. And we can focus in the case of G1, we can do this for any GI. You can always reduce to the case, you can concoct a Lie algebra, a smaller one in which the GI is a G1, right? So let's just study the pre-homogeneous vector space G0, G1, and let omega be the open orbit. We said these are pre-homogeneous vector spaces, so there's always an open and dense orbit. And the thing is, because G0 is the centralizer of this grading element, there is a character that you can define on the Lie algebra of G0, right? And this character is just pairing, this character that I'm alluding here is just pairing for an element X, you just pair using the Killing form with zeta. But now we want to define this character in a more canonical way, something that does not depend on the Killing form. And then you have to normalize it by, but don't get worried about this. It's just we get a specific character of the Lie algebra G0. And this character is exactly what I'm saying is pairing B zeta with the element X. And then you just normalize it by some fixed thing that depends on the grading. Yeah, it's a fixed number, right? And this is just given by some longest root, the root theory, but this is a fixed number that is determined by the specific grading that you have. Yeah. I mean, some people complain, say, oh, well, if you want to normalize to put this in the quotient, right? And of course, that's absolutely right. But there is a little abuse here because this B is the Killing form of the Lie algebra, while the roots are elements in the dual Lie algebra, right? And so this Killing form is really the Killing form acting on elements in the dual, right? So this, in effect, will go to the quotient. There's abuse notation. Anyway, the point is that for this pre-homogeneous vector space, and I said in the theory of pre-homogeneous vector spaces, you want to hunting these characters that are characters that have relative invariance, and you'll see why. I'm saying that in this case, there is a preferred character that is given by this grading element, and this is a Toledo character, right? A collaborator, a bit embarrassed to see the name here, but this has been appearing, his name in relation precisely to the study of the Miller-Wood inequalities in the context of character varieties or groups, real groups that are of a Hermitian type. That is that the symmetric space is a Kähler manifold. And so there was no remedy to this. This had to be called Toledo character. And so now the thing is, once you have the Toledo character, it is just given to you, just got given, right? Then you can define something that we call the Toledo rank of any element in G1. Remember, G1 is our vector space where G0 is acting. And so the way to do this is, okay, you give me an element in G, I have my element G1, I am going to complete it to an SL2 triple where H is in G0 and F is actually in G-1. This can always be done. And an SL2 triple means that the Lie algebra generated by these three elements is actually an SL2C, right? It's an SL2 Lie algebra. subalgebra of G. And this can always be done. And so this H is in G0, and you define the Toledo rank of phi as actually the valuation of the Toledo character on this H. Just you have to divide it by this thing here. And in particular, you define the Toledo rank of the pre-homogeneous pair, the pre-homogeneous vector space pair, by the rank of any E in the open orbit. So this is a number. Right? When you work with things related to the Hermitian case, this is the rank of the symmetric space, right? But this is a more general concept. Well, this is a bit, Lie theory, I don't know. I mean, it's not, I mean, you have to hope it's clear, right? I mean, you have this, once you have the grading, you have this canonical character, Toledo character, and once you have a character for any element in G1, you can evaluate its rank, and in particular, you have a notion of rank for the pre-homogeneous vector space. Now, what is this good for? Now, suppose we have and why are we interested in this actually? I mean, I said some motivation related to things that have the right to be called vortices, but also I want to put, there may be other things, but these ones are in service to the modular space of Higgs bundles, as you will see. And so consider the asset grading and consider actually all these pairs. I did this Toledo thing for G1, but the same happens for any GI, right? And so I have my Higgs pairs, where remember, E was a G0 bundle and phi was a section of the associated GI bundle twisted by K. And I want to twist it by K, as you will see. So if I can extend the structure group and define a G Higgs bundle out of this by considering the extension of the structure group G0 to the whole G, that remember was a semi-simple group. And phi is in the piece GI, but I can just consider the other pieces, the Higgs field to be 0, and this gives me a Higgs bundle. And so these Higgs bundles have a special name. They are called Hodge bundles, and this is a Hodge bundle in particular. When something reduces to this, is called a Hodge bundle of type G0 GI. Right? So I give you a G Higgs bundle, and this may reduce or not to something like this. When they reduce to something like this, these are called Hodge bundles. And this, in fact, here is a result of Simpson that states that why we're interested in this is because the C star fixed points, remember C star acts on the modular space of Higgs bundles by rescaling the Higgs field, are given precisely by these objects. So Hodge bundles are the fixed points for the C star action. So that's why you're interested in this. And then for some grading, right? I mean, if I give you a fixed point of the modular space of Higgs bundles, you can always find a particular grading so that the fixed point is like this, right? And Hodge bundles have an importance in their own in the connection to not only because they are fixed points and so on, and as we have seen, they will tell us something about the topology of the whole modular space of Higgs bundles, but also because they relate via the Nonabillian Hodge correspondence. These are correspond to flat bundles whose holonomies are complex variation of Hodge's structure, right? And these are very important objects in many fronts. Now, so why is nice to have this Toledo character? Now, let's come back to G1, and so you have a Higgs pair, G0, G1 Higgs pair. So this is a G0 bundle, and phi lies in G1 to the canonical, maybe the canonical or any other line bundle, including the trivial bundle. And then we have the Toledo character associated to this. And actually, you want to lift this invariant to an invariant of the group, G0. And you cannot always do that. You may do it or may not, but you can always find a sufficiently large rational number or integer so that you can lift it to a character of the group. And why is that good? Because once you have this lift to a character of the group, you can define an invariant of this Higgs pair. And this invariant is basically, I have this character, so I have my G0 bundle, I have this character, so this character gives me a line bundle, and I can take the degree of the line bundle. If the original character lifted to the group, then that's it. That's what we call the Toledo invariant. Otherwise, you have to divide again by the Q you multiplied with. And so this is why in many situations, the Toledo invariant is actually a rational number, not an integer. This is a particular case. And so here is the theorem that we proved in our paper, and that, let me go back to this. Is everything clear so far? Here? Any questions? Question? No, the point. No, the thing is, E is a G0 bundle, right? And you need, if you want to define degree, so first-gen class, if you have a character of G0, you have a line bundle. This thing here, this is what I should just say, this is the degree of the line bundle associated to this character. This is what I mean by this, okay? And that's an integer, and then I have to divide again by the Q I was multiplying. So define. Any other question? Okay, so this is the result that one result we prove in our paper is that if Phi is a G0, G1 Higgs pair over our compact Riemann surface, and now I'm going to, even though I have been assuming all the time that we were twisting by K, I want to give you the formula when there is no twist by K. So we're twisting by a trivial line bundle, the case of triples and so on. Otherwise, there is an additional term that involves the genus, right? Like in here, there is something that involves the genus, but this is exactly closer to the kind of thing we have been considering. And so now remember that the notion of stability for this kind of pairs, we gave a general notion of stability, was governed by something that was you take the Lie algebra, or in this case of G0, the Lie algebra, so G0, you take the center, right? And you divide it into the real and imaginary part, and you take something in the imaginary part. Well, here we are taking, so that was sigma. So we are taking a particular sigma, which is actually alpha times the grading element. So this is a particular, the notion of stability that we have for these objects, there are many more parameters in the story, many more, as many as actually governed by the center of G0. But here is one line, one line of parameters, a real line of parameters, right? A real parameter that we have singled out because it's just a multiple. This real is just the multiple in the grading element. So we will be considering, I say alpha semi-stable, I should say sigma semi-stable, but let me abuse the notation because this sigma is alpha times this grading element that is in the center of G0, the Lie algebra of G0. And the result is that if this object is semi-stable, then the Toledo invariant is bounded like this, right? Is bounded by this thing. This is like a fixed number given by the grading. And here it appears the rank of phi, right, with respect to this Toledo rank. And phi is an element that takes values in G1. And remember that we were able to define rank for any element in G1, but this is a Higgs field. And so the Higgs field generically takes values in some particular, so in other words, this, when you evaluate it on a point on the Riemann surface, is an element in G1, and that rank is the same for any generic value of X in the Riemann surface. So it makes sense to talk about rank. In fact, when we are in this kind of examples related to matrices and so on, that's the rank of a matrix. But in general, it's something abstract that is not necessarily a rank of a matrix. It's something that you can interpret in terms of Lie theory. Now, I'm presenting this inequality like this because we were interested in the bounds for the Toledo invariant, right? And because we really want to study these moduli spaces and see, counting components, studying the motive, the cohomology, or whatever, right? But from our perspective and linking to the vortex parameter, let me present this in a different way, which is that call alpha little m, and this notation should be suggestive of what I use in the case of triples. This Toledo invariant, which is a topological invariant of the Higgs pair, right, by this number, which is fixed by the grading. And then you take alpha capital M, again, this Toledo invariant, topological thing, divided by this, right? And I will say this defined like this: if G0, G1 is non-regular, where this thing, G0 hat, G1 hat, is a maximal regular prehomogeneous vector space. You see, I haven't explained this, but if in this particular case of prehomogeneous vector spaces arising from gradings, if something is non-regular, there is always a largest regular thing there. This is similar to what happens in the case of symmetric spaces of Hermitian type, non-compact symmetric spaces. There is this notion of being tube and non-tube. And this has to do with the bounded symmetric domain realization of these symmetric spaces. And this tube and non-tube plays a very important role in the theory of particular character varieties for the fundamental group into real groups of Hermitian type, is generalized in these conditions, regular and non-regular. So in the case of, like, for example, if you take the real group UPQ, UPQ for P different than Q is non-regular. But there is always a maximal regular thing inside. And this is UPP. It's similar kind of thing here. And so it's a maximal regular. So this is the alpha M, the largest alpha capital M, or infinity, if the prehomogeneous vector space happens to be regular. Because if G0, G1 happens to be regular, then this is just the rank of that prehomogeneous vector space. And it so happens that that is equal to this. And so this is 0, right? And so then the statement in terms of the stability parameter is that this stability parameter is bounded by this alpha M and capital alpha M. And why is this good? Why is this interesting, or what is happening here? The point is, you want to study these moduli spaces of fixed points and the sister action, the moduli space of fixed bundles, these Hodge bundles. And you have, and this depends on parameters, not just the Toledo invariant, but other parameters, that have to do with the center of G0. And somehow this defined some kind of chamber structure. There is some kind of
Oscar, yeah, you are a few minutes over time. So,
yes, I will finish in 1 minute. Yeah. So you have the chamber structure, right? And so you want to study a particular moduli space that is somewhere in one chamber. And it's just tremendous. How do I go to the chamber? And what this is telling you is that there is a particular line that you can follow. And this line is given by the Toledo character. And this is the line you can follow to go, as we did in the case of triples, to make this alpha large. And then it so happens that in the case of triples, you can actually describe this moduli space and then go back following that path. This gives you a particular linear path in the space of chambers. I finish here.
Okay, we have a few minutes for questions. We don't have any, so let's thank Oscar again. And